Welcome to this coding walkthrough. Today, we'll dive into LeetCode problem number 562, longest line of consecutive one in matrix. In this problem, we aim to find the longest sequence of consecutive ones in any direction, horizontal, vertical, diagonal, or anti-diagonal, in a binary matrix. Let's explore the problem, break it down step by step, and uncover the best approach to solve it. In this problem, you are given a binary matrix, which is essentially a grid containing only 0s and 1s. Your task is to determine the longest sequence of consecutive 1s that can be formed in the matrix, but with an important twist: the sequence can take one of four different directions. First, it can be horizontal, which means all the 1s are in the same row. Second, it might be vertical, with all the 1s in the same column. Third, it can occur diagonally, where the 1s follow a top left to bottom right path. Finally, it can follow an anti-diagonal direction, where the path goes from top right to bottom left. The input is this binary matrix, represented as a list of lists of integers, and the output is a single integer indicating the length of the longest line of consecutive 1s in any of these directions. Let's explore some examples to clarify this further. In the first example, the input matrix is a 3x4 grid. The longest line of consecutive 1s here is vertical and can be found in the second column, where there are three 1s stacked on top of each other. Thus, the output is 3. Now, in the second example, the matrix has a horizontal line of 4 1s in the very first row, which is the longest sequence across the entire grid. Therefore, the output for this case is 4. These examples illustrate how different directions can yield the longest line, depending on the arrangement of 1s in the matrix. In the third example, the input matrix forms a diagonal line of 1s that stretches from the top left corner to the bottom right corner. This diagonal contains 3 1s, which is the longest consecutive sequence in this case, so the output is 3. These examples highlight the importance of checking all four possible directions, horizontal, vertical, diagonal, and anti-diagonal, to find the longest line of consecutive 1s. Each direction must be carefully evaluated to ensure we capture the maximum length. To complete the problem statement, let's consider the constraints and edge cases. The matrix dimensions, m and n, can range from 1 to 10,000, meaning the solution must handle very large inputs efficiently. Each element in the matrix is guaranteed to be either 0 or 1. For edge cases, consider a matrix of size 1x1, which could have a single 1, resulting in an output of 1. Another edge case is a matrix with all zeros, where the output would naturally be 0. You might also encounter scenarios with multiple lines of 1s of the same maximum length. Here, the solution should correctly identify the maximum length and not double count. Finally, for very large matrices, the algorithm must be optimized to avoid performance issues while traversing and calculating the longest line. These considerations ensure the solution is robust and handles all types of input effectively. To tackle the problem of finding the longest line of consecutive ones in a binary matrix, we first consider a brute force approach. The main idea here is to traverse every cell in the matrix and, for each cell, check all four possible directions: horizontal, vertical, diagonal, and anti-diagonal. As we check each direction, we count the consecutive ones and keep track of the maximum length found. However, while this method is intuitive, it is computationally expensive. For each cell, we need to explore up to 4 directions, and since the length of each direction can potentially span the entire matrix, this results in a time complexity of m*n*, max, m*n*. This inefficiency becomes especially problematic for larger matrices due to the redundant computations involved. For example, overlapping cells and directions might be recalculated multiple times, making this approach impractical for competitive programming or real-world scenarios. To overcome the inefficiencies of the brute force approach, we turn to an optimized dynamic programming solution. The key idea is to use a DP table to store intermediate results for each cell, effectively avoiding redundant computations. Specifically, we define a 3D DP array, where for each cell, we track the longest line of consecutive ones ending at that cell in all 4 directions. These include horizontal, vertical, diagonal, and anti-diagonal lines. Using transition relations, we can update the DP values for a cell based on the values of its neighbors. For instance, if a cell contains a 1, its horizontal DP value depends on the horizontal DP value of the cell to its left, plus 1. Similar logic applies for the other directions, leveraging the relationships between neighboring cells. This approach processes each cell only once, leading to a time complexity of O(m*n). However, the DP table requires O(m*n) space, which can be significant for very large matrices. While this method is efficient in terms of computation, its memory usage is a potential limitation. To address the high memory usage of the standard DP approach, we can further optimize the solution by reducing the space complexity. Instead of maintaining an entire 3D DP table, we store only the current and previous rows of DP states or other relevant states. This drastically reduces space requirements to O(n), making it more suitable for scenarios with constrained memory. Importantly, the time complexity remains O(m*n), as we still process each cell once. However, this comes at the cost of added implementation complexity. Managing reduced states and ensuring correctness in all four directions can make the code harder to understand and debug. Ultimately, while this space-optimized approach is efficient and memory-friendly, its increased complexity may not always be justified, especially when clarity and maintainability are priorities. For this reason, we opt to use the standard DP approach as our chosen strategy, as it strikes a balance between efficiency and simplicity, making it the most practical solution overall. The key insight for solving this problem lies in breaking it into smaller, independent subproblems for each direction. This enables us to leverage dynamic programming to avoid redundant computations. By focusing on the relationship between a cell and its neighbors, we can efficiently compute the longest line of consecutive ones for each direction. When considering the trade-offs, the brute force method, while easy to understand, is computationally expensive and impractical for larger inputs. The standard DP approach offers a good balance between performance and simplicity, but its memory consumption may be a concern in some situations. On the other hand, the space-optimized DP approach is highly memory efficient but at the cost of added implementation complexity. By choosing the optimized DP strategy, we achieve a solution that is both efficient and maintainable, making it well-suited for a variety of input sizes and problem constraints. In this problem, we are tasked with finding the longest line of consecutive ones in a binary matrix, where each line can span in one of four possible directions: horizontal, vertical, diagonal, or anti-diagonal. For example, a horizontal line would consist of consecutive ones along a row, while a diagonal line would stretch from the top left to the bottom right of the matrix. To solve this, we start by validating the input. If the matrix is empty or has no rows or columns, we simply return 0 since no lines can exist. Next, we initialize our primary data structure, a 3D dynamic programming array called DP. This array helps us track the longest sequence of ones ending at each cell for each of the four directions. Specifically, DP ij0 will store the length of the horizontal line ending at cell ij, while DP ij1, DP ij2, and DP ij3 will store the lengths for the vertical, diagonal, and anti-diagonal lines, respectively. This setup allows us to efficiently compute and store intermediate results as we process the matrix. To find the longest sequence, we also initialize a scalar variable, max_length, to keep track of the maximum length encountered so far. Now, as we iterate through each cell, ij, in the matrix, we check if the current cell contains a 1. If it does, we update the DP array for each of the four directions. For the horizontal direction, the value at DP ij0 is updated based on the value of DP ij10 from the previous column, or it is set to 1 if this is the first column. Similarly, the vertical value, DP ij1, depends on the cell directly above, while the diagonal value, DP ij2, depends on the top left cell. The anti-diagonal value, DP ij3, is updated using the value from the top right cell. At each step, we compare the values in DP ij with max_length and updated if a longer sequence is found. Once all cells have been processed, the value of max_length represents the length of the longest line of consecutive ones, which we return as our result. The key insights here are the efficient use of dynamic programming to avoid redundant calculations and the direction-specific tracking, which ensures that we handle all four orientations correctly. Proper boundary checks, such as initializing sequences to 1 when a preceding cell doesn't exist, are also critical for correctness. The solution relies on two primary data structures, the 3D DP array and the scalar variable max_length. The DP array stores the intermediate results for each cell and direction, and its size is proportional to the dimensions of the matrix. This ensures that our space usage remains within manageable limits. The max_length variable allows us to track the longest sequence dynamically, avoiding the need for a separate pass over the DP array at the end. As for complexity, the algorithm achieves a time complexity of O(m*n), where m and n are the dimensions of the matrix, since we process each cell once and perform constant work per cell. The space complexity is O(m*n) due to the DP array, which has 4 entries for each cell. To understand the algorithm in action, consider an example matrix where the input contains both isolated and connected ones. For instance, in a 3x4 matrix with ones clustered in specific patterns, we can observe how the DP values are computed cell by cell in each direction, and how max_length updates as longer sequences are discovered. Let's walk through the given example step by step. We start by initializing the DP array and setting max_length to 0. At cell 0, 1, which contains a 1, we calculate the horizontal, vertical, diagonal, and anti-diagonal values, all of which are 1 because this is the first one in each direction. We then update max_length to 1. At 0, 2, another 1, the horizontal value becomes 2 because it extends the sequence from 0, 1, while the other directions remain at 1. Max_length is updated to 2. We continue this process for all remaining cells, updating the DP values and max_length as needed. By the end, the longest sequence is found to be 3, occurring along the diagonal direction. When considering edge cases, we handle scenarios like matrices with number ones, where the result is simply 0, or matrices filled entirely with ones, where the algorithm efficiently computes the maximum possible sequence. For single rows or columns, the direction-specific calculations ensure correct results without any special handling. Finally, to optimize further, we can reduce space complexity to O(n) by keeping only the current and previous rows of the DP array, as each state depends only on the immediate prior state. Additionally, we could implement an early exit if max_length reaches the maximum possible size for the matrix. Here, we start by defining the longest line function inside our solution class. The function takes in a 2D binary matrix mat as input. The first condition checks if the matrix is empty or if it has no columns, in which case we immediately return 0 since there are no lines to evaluate. Next, we determine the number of rows and columns in the matrix and initialize a variable max_length to 0. This variable will keep track of the longest line of consecutive ones we find. To efficiently calculate the length of lines in all 4 possible directions, we create 4 dynamic programming arrays: dp_horizontal, dp_vertical, dp_diagonal, and dp_antidiagonal. Each array has the same dimensions as the input matrix and is initially filled with zeros. These will help us track the length of consecutive ones ending at each cell for horizontal, vertical, diagonal, and anti-diagonal directions, respectively. Then, we use a nested loop to iterate through each cell of the matrix row by row and column by column. If the current cell contains a 1, we start updating our DP arrays for each direction. For a cell containing a 1, we first calculate the horizontal line length by looking at the value to the left in the dp_horizontal array. If we're in the first column, the value is simply 1. Similarly, the vertical line length is calculated by checking the cell above in dp_vertical, defaulting to 1 if we're in the first row. For the diagonal direction, we look at the top left cell in dp_diagonal to determine the length, or set it to 1 if we're in the first row or first column. Finally, the anti-diagonal length is determined by checking the top right cell in dp_antidiagonal. If we're on the topmost row or the last column, it also defaults to 1. After updating all 4 DP arrays for the current cell, we update the max_length variable by taking the maximum value among the current lengths from all 4 directions. This ensures we always have the longest line of consecutive ones encountered so far. Once the loops are complete, we simply return max_length as the result. This approach ensures that we efficiently calculate the answer in a single traversal of the matrix. Here, we begin the implementation of the solution in Java. The method longestLine takes a 2D matrix mat as input, where each element is either 0 or 1. The first step is to handle edge cases by checking if the matrix is null or empty. If it is, we simply return 0 since there are no valid lines of ones. Next, we initialize some variables, rows and cols to store the dimensions of the matrix, and max length to keep track of the longest line of consecutive ones found so far. To efficiently calculate the lengths of consecutive ones in different directions, we define four 2D arrays: dp horizontal, dp vertical, dp diagonal, and dp anti-diagonal. These arrays will store the running counts of consecutive ones for each cell in the matrix, specific to horizontal, vertical, diagonal, and anti-diagonal directions respectively. Now, we iterate through each cell in the matrix using nested for loops. If the current cell contains a 1, we calculate the length of consecutive ones in the horizontal direction by checking the value to the left in the dp horizontal array, adding 1 to it, or starting fresh at 1 if it's the first column. Similarly, we calculate vertical lengths by referencing the value above the current cell in the dp vertical array and adding 1, or starting at 1 for the first row. For diagonal lengths, we check the top left cell in the dp diagonal array, and if it exists, we add 1 to its value, otherwise, we start at 1 for the topmost or leftmost cells. We then calculate the anti-diagonal lengths, which represent the top right to bottom left direction. This is done by referencing the top right cell in the dp anti-diagonal array. If the row is greater than 0 and the column is less than the maximum column index, we add 1 to the value from that cell, otherwise, we start at 1. After calculating the lengths in all four directions for the current cell, we update the max length variable. This is done by taking the maximum of its current value and the values computed for each of the four directions. This ensures that max length always holds the length of the longest line of consecutive ones encountered so far. Once all cells in the matrix have been processed through these nested loops, the final value of max length will represent the length of the longest line of consecutive ones in any direction. Finally, we return max length as the result. This method ensures that we efficiently check all possible lines in the matrix using dynamic programming while keeping the solution clean and optimized. Here, we start with a simple 3x3 matrix as input. The goal is to find the longest line of consecutive ones in any direction, horizontal, vertical, diagonal, or anti-diagonal. To do this, we first initialize the variables. The number of rows and columns are set to 3, and the max_length variable, which will track the longest line of ones, is initialized to 0. Additionally, we prepare four dynamic programming arrays: dp_horizontal, dp_vertical, dp_diagonal, and dp_antidiagonal. Each of these arrays is a 3x3 matrix filled with zeros, and they will help us track the lengths of consecutive ones in their respective directions. Now, we start processing the matrix cell by cell. For the first cell, 0, 0, the value is 0, so no updates are made to the dp arrays. Moving to cell 0, 1, we see the value is 1, which means we'll begin updating our arrays to reflect the start of a consecutive sequence. At cell 0, 1, the value is 1. For the horizontal direction, the value in dp_horizontal 0, 1 is updated to 1 because there are no preceding ones horizontally. For the vertical direction, dp_vertical 0, 1 is also set to 1, as this is the start of a vertical sequence. Similarly, the diagonal and anti-diagonal values, dp_diagonal 0, 1, and dp_antidiagonal 0, 1, are both updated to 1. At this point, the max_length is updated to 1, reflecting the current longest line of ones. Now, at cell 0, 2, the value is still 1, so we continue updating the dp arrays. For the horizontal direction, dp_horizontal 0, 2 becomes 2, as it extends the sequence from 0, 1. The vertical, diagonal, and anti-diagonal values remain 1, as there is no consecutive sequence in those directions. The max_length is updated to 2. At cell 1, 0, the value is 1 again. Here, the horizontal value is initialized to 1, the vertical value is updated to 1 by extending from the cell above, and the diagonal and anti-diagonal values are also initialized to 1. For the anti-diagonal direction at cell 1, 0, however, we find that it extends the sequence from 0, 1, so dp_antidiagonal 1, 0 is updated to 2. This keeps the max_length at 2, as we haven't yet found a longer sequence. The process continues similarly for the remaining cells, with each DP array updating based on the values in the matrix and the relationships with neighboring cells. By systematically applying these updates, we eventually determine that the longest line of consecutive ones in this example matrix is 3. The final value of max_length reflects this result. Next, we move to an edge case where the matrix contains only zeros. In this edge case, since all the cells in the matrix contain zeros, there are no updates to any of the DP arrays. Each value in the DP arrays remains 0 throughout the traversal, as there are no sequences of ones to track. As a result, the max_length variable also remains 0, indicating that no lines of consecutive ones exist in the matrix. This example highlights how the algorithm efficiently handles cases with no valid sequences. Now, we examine a more complex 4x4 matrix that contains a mix of ones and zeros. In this 4x4 matrix, we observe both short and long sequences of ones. For instance, at cell 0, 0, the horizontal, vertical, diagonal, and anti-diagonal values all start at 1. At cell 0, 3, the anti-diagonal value is also updated to 1. Moving to cell 1, 0, the vertical value is updated to 2, as it extends the sequence from the cell directly above. As we continue processing the matrix, the updates to the DP arrays reflect the growing sequences of ones in various directions. Eventually, we find that the longest horizontal line appears at cell 3, 3, where DP_horizontal 3, 3 reaches 4. The final result for this matrix is a max_length of 4, representing the longest line of consecutive ones. This demonstrates the versatility of the DP approach in handling different input patterns. Each DP array effectively tracks the sequences in its respective direction, allowing us to determine the global maximum by the end of the iteration. The time complexity of this solution is O, rows * calls, where rows and calls represent the dimensions of the matrix. This is because the algorithm uses nested loops to traverse every element of the matrix. Specifically, the outer loop iterates through all the rows, and for each row, the inner loop iterates through all the columns. This results in a total of rows multiplied by calls iterations. So, regardless of the data within the matrix, the traversal step alone ensures an O, rows * calls, time complexity. In addition to the traversal, the algorithm also updates values in 4 dynamic programming arrays for each cell when the value is 1. These updates include the horizontal DP, which uses the value from the previous column, the vertical DP, which depends on the value from the row above, the diagonal DP, which refers to the top left diagonal cell, and the anti-diagonal DP, which uses the top right diagonal cell. Each of these updates is performed in constant time, and at most 4 such updates occur per cell. After these updates, the algorithm calculates the maximum of these 4 DP values for the current cell and updates the max_length variable. This step is also constant time per cell. Since the traversal dominates these constant time operations, the overall time complexity remains O, rows * calls. The space complexity of the solution is determined by the use of 4 auxiliary dynamic programming arrays. These arrays DP_horizontal, DP_vertical, DP_diagonal, and DP_antidiagonal each have the same dimensions as the input matrix, meaning rows * calls elements per array. Since there are 4 such arrays, the total space used by these is 4 times rows * cols. The input matrix itself is not modified, so no additional memory is allocated for it. Apart from these, the algorithm uses a few scalar variables like rows, calls, and max_length, which consume only constant space. Therefore, the dominant term in the space complexity is due to the DP arrays, resulting in an overall space complexity of O, rows * calls. The time complexity of the algorithm remains O, rows * calls, regardless of the structure of the input matrix. In the best-case scenario, where the matrix contains only zeros, the algorithm still traverses all cells but performs no DP updates. In an average-case scenario with a mix of ones and zeros, DP updates are performed for cells containing ones, but the traversal time dominates. In the worst-case scenario, where the matrix is entirely filled with ones, DP updates occur for every cell, but the time complexity remains O, rows * calls, due to the traversal step. Comparing this to a brute force approach, which would check every possible line starting from each cell, the time complexity would be O, rows * calls * max, rows, calls, as we would need to traverse potentially long lines for each cell. The current DP-based solution significantly optimizes this by avoiding redundant calculations and leveraging intermediate results stored in the DP arrays. To further solidify the time and space complexity analysis, let's denote n as rows multiplied by cols, the total number of elements in the matrix. The nested loops ensure all n elements are traversed, contributing O(n) to the time complexity. For each cell, constant time DP updates and maximum calculations are performed, which also contribute O(n) in total. Hence, the overall time complexity is O(n), equivalent to O rows * cols. For space complexity, the 4 DP arrays each require O(n) space, leading to a total space complexity of O(n). This proves that the algorithm is efficient in both time and space, scaling linearly with the size of the input matrix. When solving this problem, there are a few common mistakes that can trip you up. First, it's crucial to account for all 4 directions: horizontal, vertical, diagonal, and anti-diagonal. Missing even one of these can lead to an incomplete solution. Anti-diagonals, in particular, are often overlooked, so make sure to explicitly handle them. Next, boundary checks are another critical detail. When traversing the matrix, especially for diagonal and anti-diagonal lines, you need to ensure that you don't access out-of-bound indices. Proper boundary conditions will prevent errors. Another common pitfall is recalculating the same lines multiple times. This is where a naive solution can become inefficient. Dynamic programming is key here, as it allows you to store partial results and avoid redundant computations. Finally, it's easy to confuse anti-diagonals with standard diagonals. Remember, anti-diagonals run from bottom left to top right, whereas diagonals go from top left to bottom right. Testing these lines separately can help catch any errors in your implementation. One important mistake to avoid is failing to reset counts when encountering a zero. If your implementation doesn't properly handle zeros, the counting logic might incorrectly include gaps in the sequence, which will produce invalid results. Always reset your counts whenever a zero is encountered. Now, for interview scenarios, efficiency should always be a top priority. Dynamic programming allows you to optimize your solution to O(m*(n), where m and n are the dimensions of the matrix, making it scalable for large inputs. Pay extra attention to edge cases during interviews. For example, you should consider matrices that contain only zeros or only ones, as well as matrices with a single row, a single column, or non-square dimensions. Additionally, be ready to explain your solution clearly. Highlight why dynamic programming was the best choice, how it reduces redundant calculations, and any trade-offs in terms of space and time complexity. This problem is conceptually related to several others on LeetCode, which can help you deepen your understanding and prepare for similar challenges. In LeetCode 221, Maximal Square, you use a dynamic programming approach to find the largest square of ones in a binary matrix. It's similar in that you're working with a binary grid, but the focus is on squares rather than lines. Another related problem is LeetCode 329, longest increasing path in a matrix, which also involves traversing a matrix in multiple directions. However, it's focused on increasing sequences rather than consecutive ones. LeetCode 764, largest plus sign, requires you to calculate the longest lines of ones in 4 directions to determine the largest plus sign in a grid. Finally, LeetCode 200, number of islands, deals with finding connected components in a binary grid, which shares some conceptual similarities with identifying paths of ones. By studying these problems, you can build a stronger foundation for solving matrix-based challenges. There are a few alternative approaches you can consider for this problem. A brute force approach involves iterating over every cell in the matrix and calculating the length of lines in all 4 directions. While straightforward, this method is highly inefficient, with a time complexity of O(m*(n) max m(n), making it unsuitable for large matrices. A more efficient approach uses dynamic programming. Here, you can create a DP table with dimensions m, n, 4 to store the length of lines ending at each cell in the 4 directions. This drastically reduces redundant calculations and achieves a time complexity of O(m*(n). To further optimize, you can reduce the space complexity by using a 2D DP table and updating values in place, bringing the space usage down from O(m*(n*(4) to O(m*(n). However, space-optimized dynamic programming can make the implementation more complex, as careful handling of updates is required. Ultimately, brute force is easier to implement but inefficient, dynamic programming is optimal but space-intensive, and space-optimized DP provides a middle ground with added complexity. Thank you for following along. To summarize, we tackled the longest line of consecutive one in matrix problem, discussed various approaches, and highlighted the importance of efficient matrix traversal. Remember to practice similar problems to strengthen your skills. If you enjoyed this session, don't forget to like, subscribe, and share. See you next time, and happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!